Great. Well, again, welcome and thanks for joining us for our webinar today. I'd like to introduce our speaker, Joel Gottlieb. Joel is a senior pre-sales analyst at D-Wave, and in that role, he works with many organizations on both training and support as they learn and advance in quantum programming. Joel has a PhD in physics from the University of Wisconsin. With that, I'm going to turn it over to Joel to get started and take us through the webinar.
Thank you, Susan. Yes, our title is Cubo, I Choose You, Building an Optimal Pokemon Team with a Quantum Computer. And my goal for this talk is that within about 40 minutes or so, you'll know a lot more about how to program the quantum computer and a little bit about Pokemon. I'm not a Pokemon expert. I know that some of you probably are, and my Pokemon work here has been vetted by a very good team of Pokemon experts, but let us know if we've got errors. In any case, here we go. So, all right, this is work done with Dr. Parker Kuklinski of NAVC, an organization in Newport, Rhode Island, who wrote the formulation of the Cubo problem that we're going to look at. And I then took it and coded it on the D-Wave quantum computer. So that's the part we want to talk mostly about, although as I mentioned, you'll learn some about Pokemon too. What is Pokemon? It is a Japanese computer game, trading card game, TV show, movie franchise, and many more things. It can be played by one person or by multiple people, online games, all kinds of things. And the popularity is continuing to this day. And there's a new movie earlier this year, Detective Pikachu, in May of this year came out. So it's really a very worldwide thing. In Japan, it's known as Pocket Monsters, Pokemon. The media franchise is owned by a consortium of 3 companies, Nintendo and Game Freak and Creatures, and Nintendo is the sole owner of the trademark. And the creator is Satoshi Tajiri, did it in 1995. And it's centered on fictional creatures called Pokemon, which human beings known as Pokemon trainers catch and train to battle each other for sport. And the one down there at the bottom of this screen is known as Bulbasaur, for example. And it's quite fun. If you just type the name Bulbasaur into Google, you will get quite a lot of detail about this creature and what it can do. Pokemon is played. Players choose creatures to form a team, and then they choose attack types, and the creatures and teams sustain damage based on the Pokemon types and attack types, based on a table that you're going to see in a few minutes. And creatures can learn so that someone else's Charmander, that's one that I didn't mention when I showed it a couple slides ago, might evolve different powers than your version. The one to the right there is called Squirtle, is another example. And I won't go into some of the more advanced things which have evolved. Pokemon, I believe, is on generation 8 at this point, and we're going to only do generation 1 today. So there's some things here that we're not going to discuss. Just that would be too much detail. So our goal really to use the quantum computer to build an optimal Pokemon team based on Pokemon battle mechanics. And what we're going to do now is talk about how you would do that. So every Pokemon has a type associated with it. Although there's a hedge here that they can have more than one type, they can actually have 2. That will come into play as we go. But some of the types are normal, fire, water, grass, psychic. And we're going to write Pokemon types as PT as we go. And every attack, as I mentioned, as you're playing the game, you attack the other person or team's Pokemon the attack type is going to be written AT, and there's a damage multiplier associated with each attack depending on, and that depends on the attack type and the defending Pokemon type. And here's an example of the table. This is a small part of the table from Generation 1. The attacks are down the left column, the left side, and across the top are the defenses. That's the Pokemon types. And so you can see, you would look up in this table if you end up with an attack of normal or something against a Pokemon of type rock. Across the top there, moving my mouse, you end up with a damage multiplier of 1/2. And we'll go into that as we go, but the actual table has gotten much bigger, and I suspect that a lot of the excellent players know this table by heart. It would not surprise me. An example of some of the battle interactions occurs, for example, if you attack a water type Pokemon like Blastoise here on the right with a fire type attack, it deals 1/2 damage. The factor is 1/2. And then Detective Pikachu here, if you hit Pikachu with an earthquake type attack, it deals double damage. That factor in the table would be 2. Then, as I mentioned earlier, a Pokemon can have 2 types, and you multiply the damage multipliers together. And that made our modeling a little bit more complicated. Blizzard, which is an ice type attack, if you attack Charizard here on the right, which is a fire and flying type, it has 2 types. It turned out that it's just, they cancel out. That one's a 2, one's a 1/2. You multiply and you get 1. But an example lower there is Gyarados on the left. If you attack with an electric type attack, it's very effective. You end up with a damage multiplier of 4 because Gyarados is water and flying both. So all of this needs to be in our modeling. And here's the statement of the problem that we wish to solve. Can we build a team of 6 Pokemon such that no more than 2 members are weak to a given attack type? That is, that the damage multiplier is bigger than 1. They sustain damage like that one I just showed you. Whereas at least 1 team member is resistant to any given attack type. So we want somebody on the team that's good. That is, the damage multiplier is less than 1 against any attack type. And the data is that in Generation 1 Pokemon, there were 15 attack types, although only 12 were reasonably used, and 32 type combinations, of which 20 were generally used in play. So this is giving us a sense that we do have, as you'll see, a pretty good number of variables, which is going to affect how the problem runs on our software and the quantum computer. A first example in understanding how we write a cubo for this, and I should say here that I'm assuming that you've seen one of our previous talks. I'm hoping that you have, where cubos are built. The D-Wave website has quite a bit of material on how to build cubos. I'm going to take this for granted here in my presentation. But consider an attack type of fire. 3 Pokemon, actually 4 if we include fire itself, are weak to fire. See the 1/2s there. Excuse me, and I just spoke incorrectly. When we talk about weak, we're saying that there is damage. That means that the number should be bigger than 1, and there are 3 in the second row. If you see there, the grass and the ice and the bug. And so the constraint will be that no more than 2 are weak to fire. And later on in a few minutes, we're going to write this with this form. The 2 means the number there. We have these variables S11 and S12 for slack variables because the constraint is that no more than 2. I will talk about that later. And then the X's for grass, ice, and bug are 0 or 1. And so we want this function to be minimized. We'll talk about that coming up. And the table that's in actual use has more columns than this because I have the combinations, as I mentioned, like fire and flying would have a column as well. Then another quick example is that consider that attack type of fire against the Pokemon. And we were talking about that at least one of them must be on the team. So in that second row, there's 4 1/2s. My analysis didn't consider fire on fire, but you can see from this equation, if you're familiar with cubos, that those are my binary variables, the water, rock, and dragon. And the slack variables are the S's. And the 1 is there because I want at least one of them on the team. So now changing the language of this, we seek to build a team of Pokemon type combinations which will satisfy the constraints and minimize some objective function. And we're going to use generation 1 Pokemon creatures, each associated with one of the selected Pokemon type combinations. And our program doesn't know those little creatures in terms of their actual names. So we're going to produce Pokemon type combinations like fire and flying. The association I'll show much later with creatures is just for fun because you often have multiple choices. The attack types that we're going to have in generation 1 Pokemon are these. As I mentioned, there are 15. And then the Pokemon types are these. And you can see that not all combinations are in play because the list would obviously be much longer. But these are the ones that are in play for generation 1. All right, to develop a cubo, we're going to start with a problem in the real world, and we're going to develop some constraints, the rules we have to follow, and then we'll have an objective function of what we want to minimize. And the general form looks like this. The minimization of an objective plus the constraints and a number known as a Lagrange multiplier, the gamma, which will be some number which will change a little bit later on. So an example of this process might be the famous traveling salesman problem where your constraints are that you can only go through a city once coming in and once going out, and the objective function is the miles, and you want to take that trip in as few miles as you can. So for example, a FedEx driver does not want to do a lot of doubling back. You want to have a path that minimizes the overall objective function. So we're going to build in the next few minutes the constraints and the objective function, and then we're going to run this cubo on the computer. And the process is that you write out the objective and constraints, convert them to binary variables, make them cubo appropriate, and finally combine. So step 1 is that I have some objective function, which I'll get in that's the 4th thing. But first, what are the constraints? The team has size 6. No more are weak to a given attack type, no more than 2, excuse me, and at least 1 member is resistant to any given attack type. What are the binary variables? They're easy in this problem. In general, it's not so easy. I like to think of it kind of as an art to come up with a good choice of variables. In this case, we just need to know if each Pokemon type combination PT is on the team or not. So we're going to do that by saying that X sub PT is 1 if the combination is on the team and 0 if it's not. And so if I do that, constraint 1 gets written this way. The team has size 6. The number of members is the sum of the x's. If you think about that, if the x's are turned on, then they count. If they're not, then they don't. So the constraint is just that I'm going to have my sum equal to 6, should minimize this, and should give me 6 members on the team. The second constraint is that no more than 2 team members are weak to any given attack type, and weak, as I mentioned before, means that the damage multiplier D is bigger than 1. And interestingly, we're going to have AT of these constraints, where AT is the number of attack types. So there's a lot of these, and so I've written that there in the 4th line, 2 minus some slack variables, which enable doing no more than 2, and then a sum of some matrix named A and multiplied by X. And A is a very simple thing. It's a matrix that is 1 if the damage multiplier is bigger than 1, and it's 0 otherwise. And so if you think about that for a second, that's going to cause any of the ones that are weak to turn on in this expression. And so that's why Dr. Kuklinski did this as a matrix. It's a nice formulation of it. Next, for the third constraint, one team member has to be resistant to any given attack type. And so resistant means that the damage multiplier is less than 1. We'll have AT of those, and they look like this, where 1 plus the slack variables is then subtracted. You take away a matrix B times the X variables, and B is a matrix which is 1 if the damage multiplier is less than 1 and 0 otherwise. So this serves to activate the particular ATs that are AT and PT combinations, excuse me, that are going to have resistance. All right, now I'm going to talk a little bit about the cost function before I put it up here, because this is a very this is where there's a lot of choice, and Dr. Kuklinski chose to do it this way. And I should point out, I didn't say it before, but this project is ongoing. I expect we will have more changes to it. So there's some life in this one, in other words. And this is our first formulation of it. But the Cubo should depend on all of the Pokemon types, since they're all possible. But also you have to include all the attack types, because some are likely to cause damage, others are not. We also included a little bit about the historical use of the attack types against the Pokemon types. And of course, it should depend on the different damage multipliers. So his formulation has the cost depending on Pokemon type, as it should, as a sum over all attack types, and you assign some score multiplied by a weight. And if you don't understand this on first view, you're not alone. I had to go over it a lot of times. It's actually very good, but I'm kind of going over it fast just because it's a little complex and it takes a few looks to get it. But the general idea here, I mentioned early on that you've got some damage multipliers of 4, and those you want to score as positive because they're going to penalize having that particular combination. And the ones where there's no damage or damage of 1, for example, the third row, I want no score because that's sort of the normal case. And then at the bottom, when the damage is 0, I'm going to put a negative number on it because I usually want to make an incentive for that to happen. And finally, here's the attack type weights that Parker Kuklinski provided for me. And the strongest ones are normal and ice, used most of the time based on the historical pattern. All right, here's the complete Cubo. And yeah, it's kind of scary looking, but it really isn't. Hopefully you've gotten some feel for this as we've gone on. And P is that gamma number I talked about earlier. It's kind of a fudge factor that I can play with that we'll have to look for in terms of running this. Now, I'm going to write a computer program to implement the Pokemon Cubo on D-Wave. To do this, I'm going to use D-Wave's Ocean API. And the Ocean API is a really very clever piece of software, an API of several different packages, which has evolved over the last 2 years. And it's written in Python for the most part with some C. It's used for Ising and Cubo problems. I didn't talk about Ising, but that's another way to solve a problem on the D-Wave. The majority of it is open source on GitHub, and we are quite welcome. We would like to welcome community contributions, extensions, and new features. There's already been a lot of it. And it's been actually, for me, quite exciting to watch this. I go back to before this was there, and I'm encouraging all of you to take a look at it. There's a lot of really clever thinking went into building this. Just a quick look at the stack. The goal is that underneath there are the, showing it with my mouse there, the QPUs, and that's quantum processing unit, and GPUs like NVIDIA eventually. As you go up the levels, you want to build stuff on the lower levels that sort of abstracts away the communication with the quantum computer. So down here, you've got simulated annealing and a D-Wave API. And as you go up, you want to start building your applications, problems suitable for the QPU, graph mapping, constraint compilation, until we get up here to the top where you've got things like traffic flows, social networks, web advertising, portfolio optimization, and there's been about 150 applications written so far. So this is exciting, and I encourage you, if you're a developer out there listening to this, find some way to get involved and help us make this thing really, really good. And then the way an Ocean program gets written is that you establish your sampler, which might be a quantum computer. It might be one of our software samplers. I'll talk about that in a minute. You make the Cubo matrix, or if you're doing Ising, the H's and J's. I'm not going into that here, but our documentation talked about it. You send the information to the sampler, and a response comes back. The quantum computer or the software sampler sends back some bit strings telling you that the qubits either ended up on or off. And it's your job at that point to write some software to interpret it and see if it solved the problem. And this is usually kind of a loop. You go back sometimes and change your formulation, and I'll talk about that as we go a little further. Here's our initial results. So I implemented this model. I used a Lagrange multiplier of 1 because I didn't know anything. And when I say I didn't use slack variables there, instead of saying more than 2, I just made it equal to 2 in that one constraint and equal to 1 in the other. And here's what I got. The top 3 are famous Pokemon, Golem and Gengar and Jinx. And then the next 3, Execute and Articuno, and Lapras, little lesser known. I put the pictures there just for fun. But the point is that Rock and Ground is a type that the program said was going to be on the team. Ghost and Poison is another type. And I just, for fun, looked up on the web and found that Golem is a Rock and Ground type, just for fun. But this is the first team. But of course, what we really want to know is, did this work? Did this satisfy this constraints? And you can see by that red check mark in the middle that no, it did not do a very good job of it. And we're going to fix this. But first, I want to explain what happened. So what happened is that my constraints basically got violated. There are cases like fire, ghost, and rock where 3 members are weak to that. We didn't want that. We wanted 2 to be weak. 1 member is weak to flying and poison and psychic. That's not enough. Nobody was weak to normal and dragon. That's not good either. And 3 team members are resistant to bug, for example. So what happened to us here is that the constraints got violated. And in general, when this happens, you have to sort of consider, what can we do? You know, in other words, here's the results. What happened to us? The constraints ended up contributing 15 each to the total sum of that cubo, and the energy was on the scale of 36. So one thing we can try first is that the constraints don't seem to be important enough. In other words, if when I run a problem, I don't make the constraints important enough, they're not going to get driven to 0, which is what I want, right? I want all of these to be 0 so that those things you saw earlier, those mathematical expressions, look like 0 and they don't contribute to the total and the constraints hold. So in this problem, the way we do that is, see this thing here, this 1 multiplying the cost. If I make that a smaller number, that's going to make the other terms, the 15 and the 15 here, more important relative to the other. And so I'm going to turn down the cost term by decreasing the Lagrange parameter. Now, an aside is that typically you put the Lagrange parameter on your constraints, but in this case, we put it on the cost function instead. And that's okay, as long as we keep our heads clear and we know to decrease it. Okay? So I go on, what happens? You know, so in other words, I run up here a series of lowering the number from 1 to some other numbers, 1/4, 1/10, 100th. What happens? Well, the resistance constraints, we can meet more of those, but the weak constraints didn't really get better. And so this is telling me that I got to do something else. I don't know what yet. And one thing, though, that I want to mention that occurred here that was very good is that some of those Pokemon creatures stayed. The Golem and the Gengar, for example, those first 2, they stayed. Those types stayed. And that's giving me some confidence that I'm on the right track. I'm just not done. And when you run your problem for the first time and you're getting answers that are bouncing all over the place and you're not seeing anything consistent, that's less inspiring, put it that way. In other words, I want to see the solutions showing up a little bit so that I can assume I'm at least somewhat on the right track. Now, what did I do so far? You've got this interesting question here. How about the quantum computer? And that's because I didn't tell you that when I ran it the first time, here I used what's called the Kerberos Sampler, which is associated with a D-Wave package called Hybrid, which was released in the last couple of months and is a new package of software which we're exploring, and I'm hoping I can motivate you to play with it also. The idea behind Hybrid down the road is that we know that a programming language like Python is very good at some things and not good at others. You want to use your quantum computer for things that it's good at and leave other things to a language like Python. And an analogy for this is how people like to send the really big problems to, say, a GPU, like an NVIDIA chip, and let Python do what it's good at. And so Hybrid is a new piece of software which is starting the path of coming up with hybrid ways to solve problems. And Kerberos Sampler is a very simple one to use that was analogous to something, if you remember, QBSolve, an earlier D-Wave software package. So now I send it to the quantum computer. I'm not using the Hybrid. what happens? Both types of constraints are violated a lot of times. This is not good. The embedding that's found by the lazy fixed embedding composite package, if you're familiar with that, it embeds the problem on the D-Wave computer and tells you what it did, which is nice. And it has to use 400 qubits over 32 variables, so we have big chains. If you're familiar with D-Wave a little bit, long chains on the D-Wave architecture don't do very well. So this is really not so good. So I need to iterate. And what am I going to do? And I've got lots of choices here. And I want to emphasize this, that when your problem runs into trouble, there's a lot of things to do to see if you can make it better. So for example, anneal schedule is a new feature that we offer. We can seek a better embedding. We can design a workflow in the hybrid architecture I mentioned. We can compare to Parker-Kuklinski's classical solution. And in the QUBO, I have some choices. I could change the score function. I could change those weights. I could change the Lagrange parameter more. But what we're going to do here is, remember how I talked early on that I had these constraints at no more than 2 team members in the weak constraint and at least 1. And I mentioned how I didn't do slack variables and how I had just set them to 2 and 1. What I'm going to do now is put the slack variables in and run the problem again. And so I'm going to add a single bit variable for each attack type to allow 1 or 2 members can be weak. And I'm going to add a slack variable for the resistance one, so it could be 1 or 2 members are resistant. And this is going to add 30 binary variables. And I'm going to use the Kerberos Sampler again, since it's easy to set up. And how did we do? I set the Lagrange multiplier, in this case, to 0.01. And by now, hopefully, you've picked up enough that those first 3 rows look familiar. Golem, Gengar, and Jinx again. But I get something down here. And I remember talking to some of the the Pokemon experts, that 2 of these down here in the bottom are pretty famous. At least I know Squirtle is. So this is sort of satisfying me that, hey, maybe this is a better result. Squirtle is of type water and Snorlax is of type normal. Again, I'll reiterate the point that these are not the ones I had to choose. There's several of type normal and type water, etc. But what we have to do is the step I mentioned. It's not so good just to sit there and say, oh, well, I've got these pictures and these answers. I've got to check if my constraints are met. And the question is, are they met by the solution? And I'm quite satisfied the answer is yes. It turns out that they got a lot better. And the only violations are below here, that nobody's weak to normal and dragon, and nobody's resistant to dragon. But in order to explain why I'm not so worried by this, I'm going to go all the way back for a second to this slide and point something out. Oops, and I went too far. Notice that the dragon row here doesn't have anybody resistant to it and has only 1 here in here. So I think this problem in terms of normal and dragon wasn't all that well set up to be complete, that is. It's well set up for the solution I got. And so I'm not worried about this with the formulation that I set up. In other words, I think we've done very well. We got rid of the majority of the problems. And so in this case, I'm happy. But going back to that list of things that are options, I could also try anneal schedule and plenty of other things. So as Susan mentioned, part of my role in D-Wave is to help people get started. And sometimes I'll see things, people saying, oh, it just didn't run well. And my response typically is, did you try some of the things? There's lots of things to try to see if the problem improves. And this one did. So it's quite satisfying. So let's conclude here. We have solved Parker-Kuklinski's model. We added slack variables. And I don't know if he's listening, Parker-Kuklinski, but if he is, pretty good insight that even though he didn't run it himself on the quantum computer, he knew enough to add slack variables. And I was pretty impressed by that. And I hope I've emphasized for you that the process of solving problems involves a lot of back and forth some of the time. It's just part of the way this works. And you can see when I talked about the ocean ecosystem, it's important to realize with a historical perspective that this is going to evolve. And we're hoping that you out there who I'm talking to are motivated by this to get yourself involved and contribute to us and our GitHub repository. Because in my experience, the best tools are things which have been just totally beaten on over long periods of time by lots of people. They just get good when that happens. And yes, I've just scratched the surface of Pokemon. I don't know if I motivated you to study it, but to me it was fun and fascinating. And then we've also just started to discuss the quantum computer, and I'm going to put in a plug here for the LEAP offer. That's the URL for it, and LEAP dates back to last fall, where we basically said, if you would like to program this quantum computer for free for a month, you can have 1 minute of QPU time for free by signing up. And a minute sounds like a joke until you realize that most problems run on the order of milliseconds. So you can do quite a lot with a minute, but even more, if you are willing to give us your GitHub ID and share it, you can have 1 free minute every month ongoing. So I always sort of encourage people to do this because, one, it's fun. If it's and I should say we don't have it in every country in the world yet, but we're working on that, and we hope that you sign up. And also, there's a whole LEAP ecosystem there that you'll see, which is looking for your input, actually. And I'm not joking, actually. As I said, tools get better when a lot of people think about them. This is my email, jgottlieb@dwavesys. Feel free to contact me if you've got any questions or comment on this. And I hope you've learned about the D-Wave quantum computer and hybrid and ocean and LEAP and a little bit about Pokemon. Thank you very much for your time.
Okay, thanks, Joel. Thanks very much. We have a number of questions that have been answered during the webinar. We have a number of others that we will do right now. Please note that within a day or two, depending on how much editing this recording needs, this will be available on the D-Wave YouTube channel, so you can find it there. We can also make the slides available as well, so you can just send us an email and let us know. So with that, a couple of questions, and actually I just wanted to ask one which had been asked and answered here, but would you explain the concept of slack variables, Joel?
So when you do a constraint such as less than or equal to 2 or 3 or some number, you have to allow the possibility that let's just consider, for example, a sum. Say it's supposed to be 6, but I say it could be, less than or equal to. That means that there's a possibility that it's 5 or 4 or 3. And if I set it up with only binary variables, I don't have any way of allowing it to be 3 or 4 or 5 unless I introduce additional binary variables, which the computer could choose to be 0 or 1. In other words, if the answer is supposed to come out, say, 4, then I might need at least 2 binary variables so that they could both take values of 1 and add to the sum that is being minimized and cause it to be that smaller number. So the formulation of it, I didn't go into in detail here because you have to look at it for a while. But I hope that explains the need for them. You're basically allowing the computer more choices, more ways to minimize a given function, and you do that by introducing more variables. So if we didn't have a problem this complicated, with a lot of variables, you often can't do it because there aren't enough. But in this case, we could do it because we added a lot of variables, but there's plenty of data to go against it.
Okay. Now we'll get to some of the questions in the Q&A box here. How did you come up with the values of the score function based on effectiveness?
Yeah, a really good question. Parker Kuklinski did that, and he told me that he did some kind of statistics on Pokemon runs, Pokemon games. What fascinates me is that how did he get those numbers? In other words, I'm not sure where he got them. I think it was using online Pokemon runs, but the true answer is I got them from him, and he did the analysis, and I'm not really sure how they originated, but I do know it was based on user use of Pokemon combinations over some amount of time.
Okay. And as a follow-up to that, is the Pokemon Cubo in a paper?
Dr. Kuklinski was writing a paper. I think it has not proceeded. I expect that, yes, this will get written up either as a white paper or some sort of journal paper or an archive paper at some point. So yes, we do hope to do that. But as I mentioned during the talk, this is work in progress. So I expect that there will be some modification. So an example of what we would want to address is that thing I showed you near the end with the normal and the dragon. That is probably not so good. We would need to look over the functions and tweak them a little. But yes, the answer is I do hope to do that, yes.
Okay. How did you interpret the result coming from the QPU to Pokemon types?
When the result comes back, it is just the types. Oh, I see. I think I see what the question is. When you get the results back, there are 32 binary variables, and they're 1 or 0, and they're lined up in a specific ordering that when you formulate the problem. The ones that are 1 are those variables X that I talked about earlier, and it tells me which ones are turned on and which ones are turned off. So, for example, it said rock/ground was turned on. And all I had to do was go to the web and look up Golem if I wanted an example of one. But basically, when you run a problem on the quantum computer, the variables that you send in, the things that you've set to those X's, let me go back to that one. It was right here at the beginning. When the numbers come back, the quantum computer's job is to give you a bit string, 1s and 0s, that say this X was turned on, this X was not turned on. And then it's your job as a programmer to say, oh, that was my particular Pokemon type, this. Now, in this problem, they're pretty straightforward. Sometimes there's a mapping that's a little more complicated. But of course, it's important when you come back after a problem to interpret the solution, make sure it maps to, here's another example, is the traveling salesman. When you come back with the bit strings, it might say, okay, drive this road for 2 minutes. Well, that's not going to be a solution in general. You have to interpret it as FedEx driver should drive here with this package first, then this package second, then this package third, things like that.
Okay. Can you use this solver to build a team optimized against a specific opposing team?
Oh, sure. I don't see why not. I think that would, it would just be in the, probably you would know what the attack types were. And yeah, I would think so.
Okay. How many qubits were needed for this problem?
Oh, that is a marvelous question. Let's go over to that here. And thank you for asking that, whoever did. On this slide, I mentioned that the embedding that was found by Lazy Fixed Embedding Composite used about 400. And if we looked at a picture of that, notice that the chain lengths there are on the order of 17. So you can kind of picture some straight lines going across. If you've got in front of you like a picture of the grid, and I don't have a picture of it on my screen, but basically these are fairly long chains. The one thing we could do, as I mentioned, as improvement is that embeddings can get a lot better. The D-Wave embedding algorithm is very, very clever, but it doesn't always give you the lowest number of qubits when you run it. So we could run multiple times and look at these embeddings and try to catch one that uses fewer qubits. Because the algorithm, there's a lot of smarts involved in there in terms of embedding this problem with a lot of variables onto the QPU.
Okay, next question. The answer comes up only with a certain probability, right? What is the typical probability to measure the solution in the end?
Okay, that is another really good question. In a problem with a lot of variables, when you have a problem like this where there's lots of different answers, you tend not to get a high probability of the, quote, right answer relative to the other ones. So as a way of explaining that, in traveling salesman, you might not have that much mileage difference for that driver. There might be a lot of solutions, and they might be close to each other. What you really want, though, when you're programming and when you're trying to find a good problem and you're trying to model that QUBO, as I mentioned earlier, is you want a problem to have higher probability of finding that solution. So we don't have, I would say, any general sense of what those numbers should be. But often, as you reformulate a problem or you change the parameters, the best solution starts to show up more relative to the others. And a way to kind of picture that is you hope that the mountain peak represented by the answer starts to get steeper as opposed to just being a hill that's a little bit higher than the others around it.
Okay, is this program made accessible as open source?
No, not at this point, but I will talk to the team that owns the repository. That's some of my colleagues. My guess is that, I have to say this, I am not an original Python programmer. I come from C. So I would guess that they will have a few comments on my Python style. And after it goes through a process to open source it, I think that would be a wonderful goal of getting it out there so that other people can run on it. If an individual does want to see it, please email me and we can discuss that, you know, getting hold of it. And I'm not immune to the same thing I mentioned before. The program will get better with a lot of people looking at it.
All right. Okay. A couple more here and then we'll wrap up. Does that imply that optimal qubit amounts could be explored and then optimized for recurring problems that are very similar?
I think in general that is a goal. I wouldn't want to make a general statement, but yeah, oftentimes embeddings that are better need fewer qubits, but I don't think that's a general statement because I don't have a background in graph theory, and I wouldn't want to say that that's always true. But I think maybe a good way to do that would be to combine drawing a picture of the embedding. The Ocean toolset has some nice functions that will use Matplotlib to draw a picture on your screen. And I would suspect that the combination of some insights into optimal embeddings combined with trying to reduce the qubit count might end up coming up with a more, I would call it even, use the word prettier, an embedding that sort of makes sense. But I think in general, that is a goal, I would say, rather than being definite about it.
Okay. And then I think the last one that we'll pick here is, if you have multiple constraints, does it make sense to use different Lagrangian multipliers for each constraint?
Oh, that is a wonderful comment. Yes, it would. And in fact, a starting point that I made here, even without mentioning it, is to use the same Lagrange multiplier. And it appears that it worked. But recently I was working on a problem where there were 3 different constraints, and it was not going to work with one Lagrange multiplier. And I kind of came to the realization that I was going to have at least 2 and probably 3. And here's another thing to try to motivate all those people out there who are good machine learning programmers. Could we develop some software in the long run that would choose Lagrange parameters for us by running them and looking for optimization? It's something we've discussed. The reason I didn't do that from the outset is that I wanted to make the simplest assumption, because if I do a lot of them, I'm going to have to look through a lot more parameter space to figure out what's optimal. So I would say that is an excellent question. Thank you for asking. The answer is yes. And it's just, when writing a problem the first time, you want to just do it as simply as you can, because as you add more of them, you start to lose insight. But I suspect that, yes, some constraints are going to be requiring to be stronger than others because they just refer to different things. So very good question.
Okay, well, with that, we're going to get wrapped up. Joel, thanks very much. And thank you to all of our attendees for taking the time with us today. You will note that we've been doing pretty much a webinar a month, and they're all available on the D-Wave YouTube channel. So take a look, especially if you want to go back and learn more about Ocean and learn more about LEAP. You can go back and watch some of the previous webinars. Again, we encourage you to sign up for LEAP and to keep watching our social media channels and sign up for getting notified about additional webinars. So thanks very much, and we appreciate you coming. Bye-bye.
Thank you. Yep.